All right, guys, we're gonna work with Taylor series. So this section is really looking at why do Taylor series even help us, right? How can we work with Taylor series and recognize Taylor series? We can use Taylor series to help us with limits, to help us see some relationships between derivatives and the resulting series, approximating definite integrals. Sometimes we can't always take the integral of something. We know it exists because it's continuous, but we can't actually find its antiderivative, stuff like that. Or can I look at a power series and then could I give you a power series and then you find a function that it represents? So I grabbed this table for you. This is the table. You'll be given this table on the test. This is the table of the different Taylor series for every function. And we'll just kind of come back to this over and over to be able to do this. So the first thing I'd like to do is just do a few limits. So for example, let's just use Taylor series to evaluate a couple of limits. So the limit as x approaches 0, let's say, of the natural log of 1 plus x minus x plus 1/2 x squared all over x cubed. So if I were to take this limit, just on a normal day, on a day in my life before I knew Taylor series existed, how sad. That was a sad time in my life. If we let x go to 0, we would get the natural log of 1 minus 0 plus 0, obviously, all over 0 cubed. And so we get the indeterminate form 0 over 0. And now I could do L'Hopital's. L'Hopital's wouldn't be horrible. And, probably going to have to do it a couple times. So this is where we could use a Taylor series to make our lives just a little bit easier. So I'm going to come up here and I'm going to notice, a lot of these functions we don't, like 1/2 x squared, its Taylor series representation is just going to be a finite polynomial because it's a finite polynomial. Same thing with the x, same thing with the x cubed, right? But what is more interesting to us? What is more interesting to us is this natural log of 1 plus x. So I'm going to come up here and I'm going to look at the natural log of 1 plus x right here and its Taylor series. And it looks like we go x minus x squared over 2 plus x cubed over 3 minus x squared, x to the 4th over 4, and so on and so forth. So I'm gonna rewrite, can't write all the terms, right? That would be impossible. But I am just going to rewrite the first couple. Now I already forgot it. I know one of them's negative. I know that. We start with x. So this guy is going to be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot, dot, dot. So let's put that in there. I don't know why I didn't just do that. And let's see if maybe we can find where this really works well is if we can see that we're going to end up getting something, I'm going to get a lot of terms that I know are going to go to 0, right? That's going to be the goal. Or it doesn't always have to go to 0. This limit could possibly not exist, and that's a possibility as well. So, the power of the dot, 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 those 3 dot, dot, dots that I put right there, of course, are an infinite series. So as we go 0, I guess I was thinking infinity before. So don't listen to me always, maybe. What can cancel? So this x and this x cancel out. This guy cancels out with that guy, right? If I put in x equals 0 right now, I still get 0 over 0. So I'm going to rewrite this a little bit. And remember, the hardest part about calculus is the algebra. So this x cubed in the denominator, I'm going to rewrite that as 1 over x cubed instead. And then I have x cubed over 3 minus x to the 4th over 4. This would be x to the 5th over 5, right? Minus x to the 6th over 6, so dot, dot, dot. And now if I divide every term by that x cubed, notice how nice this is. I would get 1/3 minus, put the x cubed in, I get x over 4, plus x squared over 5, then I would get x cubed over 6, and every other term in this infinite series is going to have an x in the numerator, right? So as I let x go to 0, all of these terms are now going to 0. I don't have to use L'Hopital's. I don't have anything that's indeterminate. And what is left over? This 1/3 don't care. That 1/3 does not care what x is doing. That is my solution. Kind of a cool way to evaluate a limit. When it looks like it should be something, super complicated when actually it really isn't. I mean, you have to know those power series, right? That's why I'm going to give you that table, but it's kind of a cool way to evaluate a limit that maybe you wouldn't think would be as easy to do. So let's look at another one. I'm just grabbing one out of the book. So we'll see if I can do it. I'm sure it's gonna be fine. Oh, I forgot those boxes, don't erase. All right, let's do one more example where you have to do a bit of a, like a little substitution, kind of. It's kind of a substitution, not like a U substitution. We're gonna do a T substitution. But it's basically to let us use the, and you could probably use this, there's probably another way you could do this, but if I look at the Taylor series for e to the x, well, notice you don't have e to the x, right? You have 1 over x. And as I look at what this indeterminate form is, you know, I would get infinity here. Obviously, x is going to infinity. 1 over x is going to 0. So you're getting e to the 0 minus 1, that's 0. So I have this indeterminate form of infinity times 0. And we know in that case, right, we have to like put 1 in the denominator, and we'll probably have to do L'Hopital's. I don't know if stuff is going to cancel or not. So let's use a Taylor series. The problem is I know, right, that e to the x, I keep moving my spot, its Taylor series is 1 plus x plus, I love this one, 2 factorial plus x cubed over 3 factorial plus dot dot dot. And notice I'm not using my summation notation right here because I know I'm not, that's not going to really help me. All right, so I don't have e to the x though, but what if I make some sort of substitution? Like what if I decided that I want e to the x, so instead of having, I'm going to use t's instead. Okay, so instead of e to the x, I could do e to the t. E to the t would just be 1 plus t squared over 2 factorial, right? It doesn't matter what that variable is. I could put smiley face if I want to. It doesn't matter. I just need to make sure I'm consistent with how that works. So if I let t equal 1 over x, then if you solve this for x, notice that would give me, multiply both sides by x. I get x times t is 1, and then divide by t. So 1 over, what, I'm going to let t equal 1 over x, but then also that means x is 1 over t. So look at what I get here. I get the limit of something. I don't know what is happening there yet, but I know that this x right here, right, I can replace with this x equals 1 over t. So that becomes 1 over t. And then e to the 1 over x, now that just becomes e to the t minus 1. And now let's look what happens as x goes to infinity. So taking this right here, that x equals 1 over t, right? If I take the limit as x goes to infinity, sorry, I meant the other one. T equals 1 over x. T equals 1 over x. As x goes to infinity, right, then what is happening to t? Well, as x goes to infinity, this guy's going to 0. So these guys are going to be equivalent. X goes to infinity. As x goes to infinity, what's happening to t? T is going to 0. So remember, this limit has to change to be the same thing as t. And now we still get 0 over 0. So I'm going to use the fact that I know. Now I'm going to be honest with you. If I were really doing this, now that that gave me that t in the denominator, I would do L'Hopital's. But we're with Taylor series, and it's a new exciting thing, and we want to use that new and exciting thing, don't you? I do too. Okay, so I'm going to put in this new Taylor series, right? We get t squared over 2 factorial. You could, you know, figure out what that 2 factorial is if you want to, but we can also just leave it t cubed over 3 factorial. And then I still have this minus 1 right here. So don't forget your dot dot dots. Those are important. I will take off if you don't have those because it's an infinite series. So if you don't have those, then you're wrong, right? It's not the actual function if you don't have an infinite number of them. Now notice those ones cancel out, and then I can divide each term that remains by this t right here, and that would leave me with 1 plus t over 2 factorial plus t squared over 3 factorial plus dot dot dot. And finally, that t can go to 0, right? And this whole thing equals 1. So kind of a cool way that we can use these Taylor series to evaluate limits. I mean, I had a good time I hope you had a good time too. I think it's kind of fun. I don't hate it. I don't hate it. I hope you don't either. Let's look at a different example that it doesn't involve limits. Okay, so we're going to look at this one now, where we actually see how Taylor series can kind of work together a little bit, or hang out together, you know, based on derivatives and stuff. So we want to differentiate the Taylor series centered at 0 for the function f of x equals sine of x squared, and identify the function represented by that differentiated series. So first, let's find the Taylor series for sine of x squared, and then we'll take its derivative. And then the idea is, once we find its derivative, can I see that as another function, right? That Taylor series. So I've come back up to what I have here. I don't need that anymore. And let's look for sine of x. So here's my sine of x, right? It's all the odd ones, which I don't know why. Probably because, well, I do know why. Sine is an odd function, so we would expect that to happen. Sine of x is x minus x cubed plus over 3 factorial plus x to the 5th over 5 factorial. So if I write that down, so I know sine of x, right, is x minus x cubed over 3 factorial. Come on. There we go. Over 3 factorial. I don't know why it puts that those blue dots, sorry. Plus x to the 5th over 5 factorial. I'm just going to give myself a few more here because I know I'm going to be working with it, right? So, you know, I want to make sure that that I have enough terms to really see a pattern about what's going on. Dot, dot, dot. Okay, so what does it mean to take, what would the Taylor series be for sine of x squared? Well, remember, this is just a polynomial. If I asked you to take, you know, sine of 4, then what would you do with every x? Every x would be replaced with 4. That's what that means to evaluate a polynomial at something. So sine of x squared, then, I'm just going to replace every single x I see with x squared, right? So every x I see is just going to be replaced with x squared, and then we'll go through. Now I'm going to use the dot, dot, dots, dot, dot, dot. So let's go ahead and write this down a little bit better, because I know I want to take this derivative. So sine, or x squared, right, minus, this would be x to the 6th all over 3 factorial still, plus x to the 10th. Remember, we multiply exponents when you raise an exponent to an exponent. This would be minus x to the 14th over 7 factorial would be plus x to the 18th, right, over 9 factorial, and then minus x to the 22nd over 11 factorial plus dot, dot, dot. Okay, and now let's take the derivative. So let's differentiate. So let's differentiate this and let's see what's going to happen. So if we differentiate, I'm just going to get 2x, right, minus 6x to the 5th all over 3 factorial plus 10x to the 9th all over 5 factorial minus 14x to the 13th all over, oh, don't do that, come on, all over 7 factorial. Again, I haven't done this one yet, and I know that seems, maybe I'm just being lazy. I could be just being lazy, but I also kind of tried to do this, I guess, just to help you see the process of how you should be doing this, right? Okay, so that's pretty cool. So let's see kind of what is happening here. So there's my differentiated power series, and now what we're supposed to do is we're supposed to try and figure out what function this is. Now here's the thing, people, you know, I mean, if you were to take the derivative of sine of x squared, which you could do, what is its derivative? We know that its derivative is going to involve cosine. So I'm going to come up here. So I'm going to be thoughtful about this, right? I don't need to magically just be able to see exactly what it is. Sometimes that, you know, you got to take your time to do that. But if I come up to cosine and I see, look at cosine here, it starts with a 1. So if I come back down to my differentiated power series, how could I get a 1 in front here? Well, I could factor out a 2x because I know, you guys, you know that a cosine is going to be involved. So if I factor out a 2x, so I would get 1 minus, now 2x from 6x to the 5th, right? That'll be 3x to the 4th over 3 factorial plus 5x to the 8th over 5 factorial, this is interesting, minus 7x to the 12th over 7 factorial, plus 9x to the 16th, right, all over 9 factorial. Maybe we won't keep all of these from now on. I think we'll call that good. I do need my dots though, minus ... And now notice if I simplify this a little bit. So remember, I know that 3 factorial is 3 times 2 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. And notice that 3 is going to cancel and leave me with just 2 factorial. Here the 5 is going to cancel and leave me with just 4 factorial. It's that whole trick that we've been doing where we pull off, I can pull a 7 off, and the remaining is 6 factorial and then cancel those 7s. All right, we're getting there. We're really, really close. So what am I left with then? I'm left with 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial, right? Minus x to the 12th over 6 factorial plus x to the 16th over 8 factorial. And if you notice cosine, if it's just the cosine of x, then my exponent should match the denominator. But I don't think it's going to be just cosine of x, because notice, for it to match, what would I have to be taking, what would I have to square with this, or what would I have to take to the 4th? I would be taking x squared and raising it to those similar numbers, right? If I want my exponent to match the number that's in my factorial. And by doing that, by showing all of this, I have shown the reader of my stuff here that what is this whole thing? Well, this right here, you guys, this right here is cosine. I just love it. But it's not just cosine, it's cosine of x squared. So what does this whole thing equal then? It equals 2x cosine of x squared, which we would expect it to equal that because we know that the derivative of sine of x squared is cosine x squared times 2x using the chain rule. I love doing stuff like that. I just think it is so cool that that power series does exactly what it should. These should all work out. They should all work out. All right, one more example and then we'll call it good. All right, so let's look, last example, I want to look at this power series. And with this power series, what I want us to do is I want to identify functions. Now we've seen power series like this before, right? So let's identify a function represented by the power series above. I probably should have said that before. Represented by that guy right there. Okay, so the thing to remember, and this is something that I always forget when I look at these, is that this reminds me a lot of a geometric series, right? I have this 4 to the k on the bottom. If I pick the correct x values, if I pick x values that are going to be maybe less than 4 or bigger than -4, I'm going to get a series that converges. And so I always forget this one, but the 1 over 1 minus x, this guy right here, you guys, that's the geometric series. And you can kind of see that, right? Because look at what we have right here. We have that x to the k. So I hope that kind of makes sense. So my goal is to identify kind of one of the Taylor series that I'm going to try and get it to look like. So somehow I believe that this power series right here is going to be represented by basically 1 over 1 minus x, but with that x just messed with a little bit. Okay, so let's kind of see what I can do with this. So first of all, if I look at k equals 0 to infinity, I need it to look a lot like what is happening here, right? I just need to figure out what did that x get replaced with instead of just x there. What was actually replaced there? And I think we can figure this out. So if I kind of mess with this a little bit, so here's the problem. The problem is that this begins at x to the k plus 1, and this down here, this 4 to the k, doesn't start at k plus 1. So what I actually want to happen is I want that 4 and the x to have the same exponent. So I'm going to multiply the top by 4, and I'm going to multiply the bottom by 4. And I've multiplied top and bottom by 4, so that actually hasn't, I haven't changed it in any way technically, right? And so what am I going to get here then? I'm going to get k equals 0 to infinity. And now what do I have on bottom? I have 4 to the k plus 1. The reason I want to have that is because now it matches with the x. And so now I can put that x and that 4 together and just raise that whole thing to the k plus 1. Okay. The other thing I can do here is I can kind of look at, okay, what about -1 to the k? What about getting that to be the same also? Well, I could, again, multiply by a -1, right? The top and bottom if I wanted to, but multiplying the bottom is kind of the same thing. So really what I could just do is I could multiply this by -1, and I could multiply this by -1, right? And if I multiply this by -1, that just adds a -1 to my exponent there. But again, why can I do that just to the top? Because what is -1 times -1? It's just 1. So basically, again, what I did was I just multiplied the top by -1, and then I multiplied it by -1 again to make it just a +1. And now you can see, what do I have down here then? I have a -4. And then instead of, I could even put these two together because they have the same exponent and make that just a -x to the k plus 1. And finally, to make this all pretty, that -4 could come out front, right? Why not bring it out front? It doesn't care what the k's are doing. And this is a -x over 4 all to the k plus 1. Again, my idea, right, is to try and get this guy to have that same starting point, that k to the x plus 1, so that I can write it in the same way. Okay. All right. There's one small issue here though. If I let's look at when k is 0, right? If k is 0, right, I'm going to get -4 times a -x over 4 when k is 0. Then when k is 1, right, and let's just take that -4 out. When k is 1, then I'm going to get that -x to the 4 squared. When k is 2, then I get that -x to the 4 cubed plus ... But what the problem is if you look up here on your power series, notice that this is just a k here, and I want that first term to be 1. All right, if I'm going to use this and say I just substituted in something different for x, I need to make sure that's going to work. So what I'm going to do is I'm going to actually factor out a -x over 4. So if I factor out a -x over 4, look at what we're going to get now. I'm going to get 1 minus x over 4, right? If I factor 1 out of here, then I'll get plus that, and so we could think of that as plus a -x to the 4th to the first power. Then I would get a -x over 4 to the second power. Then I would get a -x over 4 to the third power. And now I'm starting this at 1, so now I can use that power series representation, right? Now I know that I have -x to the 4th to the k, where k starts at 0 and goes to infinity. And because I've got it in that form now with not the k plus 1, but just the k, I know that this is going to converge to 1 over 1 minus x, but since it's not x anymore, it's a -x over 4. I know, it's a lot. You got to practice these, right? So again, instead, there's what this power series converges to, 1 over 1 minus x, but I know it's not x anymore. It's the -4. So let's pull this all together and see kind of what happens. These 4's can cancel out, right? The pluses become just a plus. So I get x times 1 over 1 plus x over 4. A really easy way to get rid of that complex fraction is to just multiply everything by 4. Why did I choose 4? Because of that guy right there. That's why I chose it. So now what do I have? On top, I'm going to get 4x, right? What do I get on the bottom? 4 plus x, because that 4 right there goes over here. Here it cancels. No, you may not cancel the 4s. You may not cancel the x's. You are done. That is it. Don't try and simplify that anymore, please. I hope that makes sense, what we did there. That one can be a little bit tricky. Look at the fun sheet. I'll put some solutions up for that. This is your last video, folks. I hope you've enjoyed. Of course you've enjoyed. What is hope? I'm sure you've watched these several times. This is probably your third time watching this right now. All right, let me know if you have any questions.